Okay, hello all you crazy people out there. My name is Michael, I like wizards and dragons and making games, and let's make some games. No wait, this isn't one of those. I've been in the habit of saying that for the tower defense thing, I'm sorry. Let's talk about lighting. So this is the end result of the last video on 3D fog, and fog can be used to add some personality to 3D scenes. Things in the distance are darker than things that are close to you until it just fades out completely. Lighting is a little bit more involved than that. There's going to be a little bit more math going on when it comes to doing lighting than there was with fog. But there's no better time to start than now. There are more things that you can do with lighting. There are more types of lighting than there would be with types of fog. Fog, you can fine-tune the math, determining how it works to make something look the way you want it to. But it generally will do more or less the same thing at the end of the day. Lighting is a lot more versatile than that. There are different types of lights you can use. You can use directional lights or point lights or spotlights. You can do it in either the vertex shader or the fragment shader. You can have it affect different materials or different textures in different ways, although, to be honest, you can do that with fog too. Anyway, I'm going to be starting out with the vertex shader. You've probably seen demos of things like smooth lighting versus flat lighting. And if I can go find a side-by-side. That is not at all what I'm looking for, thank you. This is what I'm looking for. Something more like this. This is flat lighting, this is smooth lighting. This is, there are different types of smooth lighting models. The one in the middle here is called Garage shading. The one on the end is Blind Fong shading. These two over here, these two are going to be a matter for another day. Right now I'm just going to be doing flat lighting in the vertex shader. So let's talk about how light works for a minute. If you paid attention in high school physics class, you're already a step ahead of me on this matter. Let's say you have a surface that's going to be illuminated and you have a ray of light. The particular kind of light source doesn't really matter. It could be directional, it could be a point light, it could be a spotlight, whatever. This is just a ray of light and it's going to interact with the surface. So without getting into the real physical physics of how a ray of light, a photon, bounces off the material that the surface is made of and is scattered in different ways. To us, the amount of light that a surface receives depends on the angle that the light hits it at. If the light hits it straight on, most of the light is going to bounce back towards the observer and it's going to appear fully lit. If the light hits the surface at an angle, not as much of it is going to bounce back at you, so it's going to be darker. And if the light hits the surface at a very low angle, if it's coming in almost parallel, then next to none of it is going to be reflected back at you, and it's going to appear very dark. And then if the surface is pointing away from the light, it's just not going to be reflected at all. So let's talk about translating that into math. So you're going to need a few things to do lighting. The first one that I'll talk about is the surface normal. I've been kind of avoiding talking about normals in past 3D videos when it comes to building vertex formats and that sort of thing. I believe in most of those cases I just said I will worry about those later, and that later happens to be now. The surface normal is the vector that is perpendicular to a triangle, or if you're working in 2D space, it's the vector that's perpendicular to a line segment, or just a line. I guess you could apply that to higher dimensions too, but since we're doing 3D computer graphics, we don't really care about like 4D surface normals. Although if you have a degree in math, you might just like do those for fun or something. Math majors are weird. Anyway, I won't talk about how to calculate the normal of a triangle at this moment. Most 3D modeling software will either do it for you automatically or actually give you some pretty granular control over exactly how they're worked out. There are equations that you can just plug in 3 points of a triangle for, and it will spit out a surface normal for you. That could be an interesting future video topic, but for the time being, I'm going to assume that you got it from the 3D modeler when you imported it or something. When it comes to vertex shaders and vertex buffers and that sort of thing, the concept of a face of a triangle of 3 vertices isn't really something that exists. So the normal vector of a face is generally attached to the vertices as a vertex attribute, even if it's going to be the same for every vertex in a triangle. They don't necessarily have to be when it comes to doing smooth lighting. Each of the normals in a triangle may have a different value that's interpolated, but that's a story for another day when I talk about smooth lighting. The other major piece of math that you're going to need to use when it comes to writing lighting shaders is the dot product. And the dot product does more or less what I just described when it comes to comparing angles. The equation for calculating the dot product looks like this, but fortunately you don't really need to implement that yourself because pretty much all shader languages ever will have it implemented for you. Anyway, as I was saying, the dot product will return information about the relationship between two vectors, about the angle formed by two vectors. If the two vectors are pointing in the same direction like this, and I'll explain how this relates to 3D lighting equations in a minute, then the dot product between the two vectors is going to be 1. If the two vectors are perpendicular to each other, if they're at a 90-degree angle, then the dot product is going to be 0. And if the two vectors are pointing in the opposite directions, the dot product is going to be -1. And if the angle between the two vectors is somewhere in the middle, then the value will be somewhere between -1 and +1. And you can use this to determine how much light a surface or a vertex should receive. A small note that's worth pointing out, the yellow vector and those little doodles, the light vector, is really the opposite of the incoming light ray. You can think of it as the light ray that's bounced off of the surface. The reason for that is that the unaltered surface normal and the light ray would normally be pointing in the opposite direction of each other. And in order to get a positive dot product, they need to be pointing in the same direction. So to get the vector you want, you just have to throw a negative sign in front of the incoming light vector. Or if you're math savvy, you can do some other arithmetic operations to turn the dot product into the value that you're looking for. It's kind of a convention when you're writing shader code to just invert the incoming light ray, though. Okay, that's enough pure math. And I hope I don't go too insane trying to create all those images in Photoshop representing like arrows and light rays and angles and that sort of thing. So as I did in the fog video, I'm going to start out hard coding the positions of different things. Speaking of hard coding, do I actually still need those? All right, fog color is used. That should probably be a uniform as well. I guess I just forgot to make that a uniform. And fog origin has been... Oh no, fog origin is used also. Since this uses the camera matrix trick instead of passing the camera position as a uniform, this is kind of not needed because that's just subtracting 0, but that'll still work, right? Yeah. All right. Don't tell anybody that I've been messing with a tutorial video after it was finished. Okay. Anyway, now that I've described that, the first thing that I'm going to do is a directional light. And I'm not going to add anything, I'm not going to add any special varyings, I'm not going to add any extra attributes or anything like that. I'm just going to use what I have, although I will uncomment the commented out normal attribute. And let's get rid of that because it's not really a pass-through shader anymore. And to determine the color, to determine the final color, I'm simply going to use the existing color varying. So let's define a few things. One is going to be a vec3 representing the light position, and that's just going to be vec3 0 0, or if you prefer 0.0 instead of just 0. It seems like not a lot of people are aware that you can just type 0 instead of like 0.0 to denote a float. I want to make more people aware of that because it's really convenient, because typing out extraneous zeros just makes your code more cluttered and takes an extra keystroke every time you type a number. Anyway, to start with, we're going to hard code the light position at 0, and that is actually all I need. I guess we can also say vec4 light color. That's going to be a vec4 1. It's going to be pure white. Alpha is all the way up, although we'll not really be using alpha here, I don't think. Maybe we will. Whatever. Actually, you know what? What am I talking about? Directional lights don't have a position. All right, if you all caught that little error before I did, good for you. I guess I was thinking of like I guess I was thinking this was going to be a point light or something. Let's make the directional light is going to be 1, 1, -1, so it's going to be, if you remember the first 3D video that I did for this series, and I had the camera starting at the room origin, some distance in the air, and I had it looking down across the room. The direction of this light is going to do essentially the same thing. So if I were to run the game, this isn't going to do anything, but if I were to run the game, the light would The light would start somewhere above my head, and it would end. It would be moving downwards to somewhere off in this direction, towards the floor. So the tops and north and west facing sides of these squares should be illuminated, and the bottom, although you can't really see the bottom, and the south and east facing sides of these squares should not be. Okay. I thought something looked a little bit funny between this code that I'm writing here and my my example on my other screen, and that would be the fact that directional lights do not have a position. Dot products. I promised dot products, and I'm going to deliver on that. So we're going to define a float as the result of the dot product. What do I want to call that? I guess I could call it like light dot or something, or light angle.
Hey.
Difference or something. I guess that's okay. That's a bit longer than I normally like to have a variable name be, but a shorter name might be a bit ambiguous. Let us say the dot product of the world normal. And the world normal, by the way, is going to be very similar to the object space position, the GL position calculation. If you ever transform an object in space, in addition to transforming its position, you also need to transform its normals. This is something that I forget constantly when I do lighting shaders, and I always end up with, for example, non-rotated objects being lit properly, but rotated objects being lit in bizarre ways, and that's because I forget to transform the lighting normals. Otherwise, you'll suddenly have a rotated object being illuminated as if the light is in some other position other than what it actually is. And same for scaling. I believe a couple people have also mentioned that in the comments of past videos. If you transform the position of an object, you also need to transform its normal. So I'm going to say vec3. Let's call it world normal. And just to make sure that I am going to actually use the correct value, let me look over here on the other screen. Okay. The world normal is going to be the product of GM underscore matrices matrix. I feel like I do that about once per video too. It's just going to be the world matrix multiplied by a vec4 containing in underscore normal, and let's just make the fourth component of the vector4 is 0, because you're not allowed to multiply a vector 3 by a 4x4 matrix. Two things about this. One, this calculation is not guaranteed to produce a vector that's normalized with a distance of 1, which is normally what we want to keep things simple. So we're going to use the normalize function, and that will keep all the proportions of the vector the same, but it will just normalize it so that it falls between 0 and 1. It has a magnitude of 1 instead of being, for example, scaled up or down if you have a scaling applied to the world matrix. And 1, this is a vector 4, and we want a vector 3. So we'll just grab the xyz component of that normalized vector, and now we can go back to the dot product. I want to know, how many people watching this video were aware that I was forgetting that stuff there as I was plowing ahead with the dot product and stuff? Either that, or how many of you have tended to do the exact same mistake when doing this sort of things. So, dot product. World normal versus the light direction. Also, by the way, this is matrix world instead of matrix worldview projection. Matrix worldview projection also takes the camera's matrices into account, so it's view and projection matrix. And that's what you want when it comes to putting stuff on the screen. But we don't need that here, since lighting isn't anything that happens relative to the camera, or at least normally it's not relative to the camera. If you want to do some weird like horror game effects, maybe that's what you want. I won't judge. The position of lights in the world don't care about the camera, so you can just use matrix world instead of the other ones. So as I said a little while ago about the dot product, this can return a value less than 0, in which case the light source will be behind the face that it's illuminating, in which case it shouldn't be illuminated anyway. So we can simply say max of the dot product and 0. We don't really want any negative numbers in this calculation, and the light behind the face will have the same effect as the light that's parallel to the face anyway. It'll be 0 all the same. And now that we have this piece of information, instead of saying the vertex color that is passed to the fragment shader is just simply going to be the color of the vertex attribute, we can say that instead that it will be the color that comes as a vertex attribute multiplied by the light color, which is in our case just 1, multiplied by light multiplied by the light angle difference. So again, if the light is hitting the face, or I should probably say the vertex at a head-on angle, the dot product is going to be 1, and it's going to be fully reflected, fully illuminated. So that's going to be the in color times the light color, which is 1, times the angle difference, which is also going to be 1. So a number times 1 is going to be the number that you started with, which is just going to be in color. If the light is parallel to the surface and perpendicular to the normal vector, parallel to the surface, or behind the surface, I should say, then the light angle difference will be 0. Anything times anything else times 0 is always going to be 0, so it's going to be black. And then if the light is going to hit the surface at some other angle, it's going to be a number somewhere between 0 and 1, which is going to be a gray as the color that's blended with the vertex. So the vertex color is going to be darkened, but not completely. Also, this also will affect the alpha value, so that could look kind of cool if a darker surface is semi-transparent, but that's not what we really want. Let's vec for. Am I allowed to just say that xyz and then 1 for the alpha value? That should do it. I think I'm allowed to use vectors like that. Okay. I hear thunder outside. Also, this is not doing exactly what I want. Okay, so this is going to be what, like 2 videos in a row where I said you all have 10 seconds to guess what went wrong here? I don't know if that was 10 seconds or not, but time's up. One, I'm going to actually not mess with the alpha value for now over here, because it actually does look kind of cool when you don't do that. 2, what actually went wrong is I missed a minus sign. When I was describing the dot products earlier, I think I said if the difference in the angles are less than 90 degrees, then the dot product will be positive, otherwise it'll be negative. At least I hope that's what I said. You may have noticed I'm pretty good at saying things backwards sometimes, and in that case I will have had to correct myself in text on the screen or something. When you look at light hitting a normal vector, you're going to want the opposite of that, because the light and the normal vector of a face, if they're head-on, they will be going in opposite directions instead of the same direction, so you just want to reverse that, throw a minus sign in front of the light direction to get the answer you actually want. Okay, you can see now whenever in the game, the side that the light is hitting all objects coming in, kind of going across the room. I will try and put an arrow on the screen that is more or less the direction of the directional light. You can see it does not like originate at any point in the room. If I move around, the side of me that is lit is not relative to the origin or anything. It's just a directional light. Point lights can be the subject of the next video because I like point lights. And the same is true for these objects over here. What were they? The northern and western faces are lit, and the eastern and southern faces are increasingly not, as you can see over here. The transparency thing is interesting. I think that's interesting. Some of you may think it's weird if you don't happen to be as much of a fan of the transparency thing. I did this before, right? So we can take the RGB of the color, the original alpha, and we can do that. And now instead of being transparent, they'll just be like darkened. Much better. No more weird transparency issues. I probably should talk about transparency in 3D at some point in time, but I really don't want to because transparency in 3D sucks. You can change the what would be the ambient light color. Oh, another issue you may notice, and I was deliberately leaving this until later, until everything fell apart, and now it just looks like I don't know what I'm doing. These surfaces of these objects that are like in direct sunlight, as it were, they are slightly too bright. Their brightness has increased past their normal value. Normally, perfect lighting should not add any light. It should not make things look washed out. At least that's not what you normally want. That is an effect of the light direction not being normalized. So if you were to get the magnitude of this value of this vector, it would be, I want to say about 1.6 instead of 1, which is normally what you want when you're looking for vectors when it comes to lighting. You can normalize that. And you can put the minus sign in front of either the vector or the normalized function. It'll do the same thing. If you want, the output of that calculation will be the same. Now, if I were to run the game, the light would not be at a. As you can see, everything is. The maximum brightness is the original color, as if it would have been unlit, because that is being multiplied by 1 instead of down here with the vector that was not normalized. Instead of being multiplied by a bigger value and making things artificially bright. If you want to do that sort of thing on purpose, if you want things in direct sunlight to be a bit washed out compared to the normal color values, you can. Specular highlights are sort of like that, except not really. It's just the closest thing that I can think of. That's also a subject that may merit its own video at some point. That is it for directional light calculations. As with fog, you most likely want to make this a uniform value. Let's see. All right, so that's just fog start and fog end. I guess. Let's give the vertex shader some extra uniforms. Uniform, vec3. I'm just going to call it a light direction, and also because why not? Because we can. That would be a vec4, the light color. So now, let's see, I will no longer be able to use the variable name light direction or light color. I don't need this one at all because that's just going to be a uniform. I will call that simply light dir. And we can replace the hard-coded direction vec3 with a uniform. I can get rid of these because those were leftovers from the video about shader uniforms, and this will be uniform instead of fog start, fog end, light direction, and light color. Okay. Let's make sure those are the correct things being given. The direction. Should I have some fun? Should I make like a rotating sun or something? Nah. I've beaten trigonometry to death so far in this series. So if you want to make like a rotating directional light to represent the angle of the sun or something, you can do that. I'm just going to make the light direction like. Let's have it go the opposite direction that it was going before. So that would be what? -1, 1, and -1. So that'll be, instead of going southeast, it'll be going southwest. Something like that. That should be good. And the color is going to be, I guess, do I want to make it like red or something? The color can be 100. On the color channels, 1 on transparency, although that won't really be doing anything. You notice this looks this looks like rather ominous. And also, you can't see anything that's not red because anything on the texture, anything in the world that does not have a red color, will not be reflecting any light, only red light. So we can make that like a bit of a softer red. How about giving the other color channels a little bit just so that you can see a little bit? No, that didn't do it. Does the grass really just not have... Does the grass really just have so little color? obviously, for one, and I've just set the color to white, the light color to white for now. For one, I am not actually using the normalized direction, the normalized light direction, or the negative light direction, the correct one that I'm supposed to be using, which will help. All right, so now it's coming in from the right angle, and now that lighting is working at all. All right, so now the light is very orange, as you can see. That's a little bit spooky, shall we say? Looks like something's gonna jump out of the shadows and eat me now or something. By the way, there's also the matter of ambient light. Ambient light is the color of the unlit faces. In real world terms, it would be the light that's scattering off other objects and illuminating things that are not in a direct line of sight to the light source. If you don't want the world to be completely black in unlit areas, you probably want that to be some sort of gray. We can account for that as well. Let's start out hard coding the value. We can say vec4 light ambient equals, let's make it like 0.25, and 1 on the alpha value, because why not? And now we can add that to the final color that's calculated with the math, the lighting math. And this will just guarantee that there's going to be that there will always be some initial color. You can see now there's a little bit of gray on the inlet side instead of black. This will also have a potential washing out effect, the same way that not normalizing the light direction did, because this could cause this value to go greater than 1 and increase the color of a vertex. So as always, whenever that's the case, you could say, what would it be, min, the minimum value of this, and 1 in the form of a vector 4, and that would prevent any washing out effects. So the light-facing sides of my character cylinder guy is no longer a little bit lighter than normal, and the unlit sides are an even gray instead of just like the abyss. Okay, that is everything I wanted to cover with lighting. At least directional lights in the vertex shader. There's a lot of other stuff I want to cover with lighting, but that'll have to wait. Next time, I'm thinking point lights. There's also the matter of having more than light running in your scene at once. In which case, instead of using a specific uniforms for light direction, color, and all that, you'd use a uniform array, which could have multiple values in it, and you would just do this multiple times in a loop. That's another thing I'll worry about later. Probably after I do point lights, and there is actually a reason to have more than one light sources in a scene. There's also the matter of spotlights. Spotlights are more complicated than point lights or directional lights, although I don't think they're like absolutely insane or anything. They're also not something I use myself too often, but I kind of feel like I should talk about them anyway because they are the third type of light that it's common to see. After that, I talked a little bit about smooth shading in the beginning of the video, and I should probably actually go into more detail on that. That would involve interpolating the normals over a surface and doing the lighting calculations in the fragment shader instead of the vertex shader. And probably after that, I can start talking about 3D object materials, because that's always a fun time, and some other things. Anyway, my name is Michael. I like wizards and dragons and making games. If you want the code for this, video description. I have a Patreon for these things, so if you want to contribute towards these videos being made a bit, there's links to that in all the usual places. Otherwise, I try to post 2 of these a week, which is currently one tutorial and one tower defense video. Let's make a game. I think that's all I'm supposed to say, and I will see you all later. Special thanks to Edward Holt, Indie Punch, and Zenith for supporting these videos. If you want your name in the credits and to force me to pronounce them out loud at the end of every video, head over to the Patreon page in the video description and join the fun.